Ladies and gentlemen, thanks for being here. I'm Xin Li from San Jose University and the University of Minnesota. I'm very happy to share my recent works on the phase change materials. The topic today is the investigation of phase change thermal management based on a pore-scale lattice Boltzmann model. Let's begin from the background and motivation firstly, and the second part is some numerical model introduction, and the final two parts is related to the important results, including the gravity effect investigation and material selection. So for the photovoltaic panel, sometimes we also call it solar cell. It's kind of the energy conversion device from the solar radiation into the electricity. So now it has been used and to supply power for the spacecraft. But for the PV panels, it's very sensitive to the temperature. And shown in this figure, the higher temperature means the lower efficiency and the lower output power. So especially it needs the thermal management for the PV panels in the space systems, because the heat environment in the space systems is very complicated and variable. The solar radiation is variable at different time at different space. So it puts forward the higher requirements for the thermal management. To these issues, that PCM, phase change material, attracts us. For the phase change materials, it's kind of the thermal management system based on the solidification and melting process. During these two processes, the most advantage of the PCM is a high energy storage density and also its stable temperature. As shown here, the heat will be absorbed as the latent heat by the PCM. So in this period, that the temperature is relatively stable. But for the most of the PCMs, they're under the poor thermal conductivity. So in order to enhance the thermal conductivity of the PCM systems, then they proposed some composite PCMs, such as that incorporated with expanded graphite and also the metal forms here. And also it has been used in a spacecraft successfully. And when we use the PCM for the PV panels, especially in the space explorations, there are also some different challenges for us. The first one is the gravity-dependent phenomena of the PCMs. For the space explorations, no matter what's the gravity conditions here, supergravity, microgravity here, it will some influence on the phase change process. And finally, it will lead to the different temperature behavior and also has a different influence on the PV panels, especially for the efficiency of the PV panel and the final output powers. So for us, it's also necessary for us to understand what's the influence of the gravity effect on the phase change materials and also the PV panels. That's the first thing. And the second challenge is the material selection. Especially for the phase change material, there are so many criteria for the PCM, such as the high efficiency, stable performance, and also compact and lightweight here. Just for the thermal properties, it's very important. It's the most important things for the PCMs, including the melting temperature, thermal conductivity, latent heat. So it's related to the final energy storage performance of the PCM. But until now, actually, no matter what kind of the material is, organic ones, inorganic ones, they also have their own advantage and disadvantage. Such as for organic ones, it has the high latent heat, but it has a lower thermal conductivity. So we need to balance when we choose it, which one should be used. Firstly, maybe the comprehensive investigation should be started firstly. It will help us to know which one is the influence factor, is the main factor for the final performance of the PCMs. With these two different challenges, we did the numerical studies firstly, and so here a pore-scale lattice Boltzmann method is used and is programmed to study on the supergravity effect on the phase change materials. And also, we did some material selection investigations. Here, we including the melting temperature influence on the energy storage performance and also the latent heat of the PCMs. So finally, I believe this work can provide the comprehensive investigation on the composite PCMs. Especially, it's good for the design of the composite PCMs for the PV panels under the space explorations. And so next, let's get into the method I used in this work. Lattice Boltzmann method is a kind of the mesoscopic method, and it has been applied to simulation of the many complex problems, including the heat transfer and also the fluid dynamics problems, such as the point boilings, porous fluids, and the thermocapacity fluids, and also the phase change in our works. Specifically, that for the phase change materials with pore structures, we use a pore-scale lattice Boltzmann method. That it means that here we use the real pore structures and there without any assumptions of the pore permeability. So under usage, we can get the detailed flow files and temperature files of the PCMs. So that's why we use it. So in this work, the first thing we should do is to get a detailed description of the structures. So here we use a metal foam as enhancers, and by using axial CT, we get 2D figures. And based on this so many 2D figures, we can get the final three-dimensional structures description in this work. And also for the PCMs, the gallium is used in this work. In this work, then the left wall here is a high, it's a high temperature, and the right wall here is a constant low temperature. So the PCM, the gallium will melt from the left side to the right side here. That's the physical model in this work. And after we get the description of the structures, so let's start a simulation of the temperature and the velocity. So here we use a double population LBM. One is for the velocity and the other is for the temperature. And the gravity effect, once I will investigate it, is described in the Boyle's force. And for the phase change, there is a latent heat as described here. Finally, we can get the velocity and the temperature under different times during the melting process. So that's what we use it, the method what we used. And for the melting process, this slide shows the temperature distribution during at different times at different flare times. This one shows the temperature distribution, and this video shows the melting interface. Then the solid one, liquid ones, and the solid ones. So here we can find at the early time that the melting interface tends to be vertical one. But as time goes by, later in the last ones here, then the melting interface tends to be inclined. So this phenomenon is caused by the natural convection because we have the clockwise natural convection. It will lead to the faster melting at the top of the PCM, but lower melting at the bottom. So the natural convection is very important as things in phase change materials. That's why we focus on the different gravities. Here we compare the temperature distribution at a Fourier number, at a certain Fourier number, and for different gravity conditions is compared here. So also with the larger gravity conditions, we have the more inclined melting interface. So this is also caused by the natural convection because for the larger gravity conditions, we have the bigger buoyancy force and also the stronger natural convection here. So the heat transfer will be dominated by the convection in this part, in this period. And this conclusion will be confirmed again by this figure. This figure will compare the velocity and different gravity conditions. So the larger gravity conditions have the bigger velocity. So it tells us the stronger natural convection under the larger gravity, under the supergravities. And also we wonder, so what's the influence on the melting rate of the energy storage. So here we compare the melting fraction. It tells us how many PCM be melted in the systems. So compare that the melting fraction under different gravity conditions we can find. For this blue ice, it has the highest gravity conditions. That it also has the highest liquid melting fraction. So it means that more PCM is melted in the super gravity conditions. It will promote the melting process under the increasing gravity. So it's good for us to have the higher heat transfer rate and larger energy storage capacity for the PCMs. That's for the gravity effect. And also we did some study on the material selection. So first one, we consider the latent heat of the PCMs. The latent heat is described in this part as the dimensionless parameters, Stephen numbers. So the higher latent heat of the PCM means the lower Stephen number. So first we compare the melting fraction under these three different Stephen numbers. We can find for the red lines, it has a higher Stephen number. It melts faster than the others. So it tells us that the lower latent heat has a higher melting rate. But also for the energy storage capacity, we have the different results here. For the red lines, that with a higher Stephen number but have the lower energy storage density. So it tells us, and it also explains why it melts faster for the red lines that with a higher latent heat, with a lower latent heat, because it just needs a lower energy to be melted. So that's for the latent heat. And also for the temperature of the melting temperature of the PCM, we also compared that under the three different ones. That's also the dimensionless temperature here we used. For the black lines, it has a lower melting temperature that is equal to the right side and the environment temperature here. It has a higher melting fraction and it melts faster than the others. So it tells that lower melting temperature have a higher melting rate. But here we can find finally that for these two cases, that PCM is just partly melted, not fully melted, just about 80%, and also the 60% melted here. So we know that energy storage capacity is very sensitive to the melting fraction. So here we also compare that in this figures. And we can find these two figures as very similar with each other. They have the similar trade and also have the similar relatively values. So this tells us, and it also indicates that the melting temperature have more influence on the melting fraction and the melting rate. And energy storage capacity here is just directly related to what's the melting fraction. So because the Stephen number here is the same with each other. So that's for the melting temperature. Okay, after that we know that higher latent heat and the lower melting temperature, the lower temperature difference here is desired for us to get the higher performance of the PCMs. But sometimes it's difficult for us to get this kind of materials have these two properties simultaneously. So for us, if we need to choose which one should be used, we need to balance the latent heat and the melting temperature. So here I want to say latent heat have the more influence on the energy storage capacity, and the melting temperature have the more influence on the energy storage rate. So it's which one should be used. It's depending on the demand of the systems, on the energy storage capacity and the storage rate. So that's what I did on the melting selections. Finally, it's a brief conclusion. So for the supergravity conditions, we can find it have the faster melting and and also it will be dominated by the natural convection on the supergravity. And for the material selections, that we can find that higher latent heat than lower melting temperature. Melting temperature is best for us, and the latent heat is have more influence on the energy storage capacity. But energy storage is more affected by the melting temperature of the PCMs. So that's the influence of the properties of the latent heat and the melting temperature of the PCMs. And in the following works, I think one thing should be do is to consider some relationship between the PV panels and the PCMs, because after that we can get the final results and the final influence on the PV panels. So that's what I prepared for that's my report here. Thanks for your attention, and also welcome comments.